I deserve an acceptable reason.
Crystallization is the formation of solid crystals within a homogeneous phase. It may occur as the formation of solid particles in a vapor, as in snow, as solidification from a liquid melt, as in the manufacture of large single crystals, or as crystallization from liquid solution. This video deals mainly with the last situation. Crystallization from solution is important industrially because of the variety of materials that are marketed in the crystalline form. Its wide use has a twofold basis. A crystal formed from an impure solution is itself pure unless mixed crystals occur, and crystallization affords a practical method of obtaining pure chemical substances in a satisfactory condition for packaging and storing. So what are crystals? A crystal is the most highly organized type of non-living matter. It is characterized by the fact that its constituent particles, which may be atoms, molecules, or ions, are arranged in an orderly three-dimensional arrays called space lattices. As a result of this arrangement of the particles, when crystals are allowed to form without hindrance from other crystals or outside bodies, they appear as polyhedrons having sharp corners and flat sides or faces. Here are some crystallizers commonly used in the industry. The first is a Swanson-Walker crystallizer. It consists of an open trough with a semi-cylindrical bottom. A water jacket is welded to the outside surface of the trough. This is an example of a continuous type crystallizer. The hot supersaturated solution is fed at one end of the trough, and the cooling water flows in the jacket but in countercurrent to the solution. The second type is an Oslo crystallizer. It is also called classified suspension crystallizer. It is the oldest design developed for the production of large coarse crystals. It is worth bearing in mind that the operation costs of the Oslo crystallizer unit are much lower than with any other type when both large and coarse crystals are required. Since crystals are not in contact with any agitation device, the amount of fines to be destroyed is lower, and so is the corresponding energy requirement. The third is a vacuum crystallizer. Under vacuum, the boiling point of a liquid reduces. So under vacuum, a liquid boils under its normal boiling point. Cooling will cause supersaturation and thus crystallization. Evaporation will increase the yield.
네, 오늘도 촬영 현장에서 함께 해주셔서 진심으로 감사드립니다. 아리가또. 저는 그래서 뉴질랜드의 매니저 형이랑 단 둘이 가는데
Here are the equations usually used in crystallization. This is the set of equations for cooling without evaporation. For the case of with evaporation of the solvent, the following formulas will be used. For vacuum crystallizer, refer to these equations. Here are some diagrams which can be of great help when solving, but you can always check your Paris handbook for other diagrams. This is the phase diagram for magnesium sulfate and water system. The enthalpy concentration diagram also for magnesium sulfate and water system. This is the solubility curves for some typical salts in water. This is the solubility of sodium thiosulfate in water.
잘 마치도록 하겠습니다. 민호의 굿데이, 굿데이.
Let us try to apply the equations and principles of crystallization to the actual problem. For the first problem, a solution consisting of 30% magnesium sulfate and 70% water is cooled to 60 degrees Fahrenheit. During cooling, 5% of the total water in the system evaporates. How many kilograms of crystals are obtained per 1,000 kilogram of the original mixture? This is an example where evaporation is involved. The following diagram illustrates the given problem, where F is the feed, V for vapor, L for the mother liquor, and C for the crystals. Note that the final temperature of our mixture is 60 degrees Fahrenheit. We can see from this diagram that it corresponds to the value of concentration of the magnesium sulfate. Our crystal is magnesium sulfate heptahydrate, and from the given diagram, the concentration of the mother liquor is 24.5% magnesium sulfate and 75.5% water. The total water in the feed is 70% of 1,000, which is 700 kilograms, and the evaporated water is 5% of the original water, which gives 35 kilograms. Getting the molecular weight for magnesium sulfate is 120.4, and for its hydrate is 246.5. First, let us perform the overall material balance. It is F is equal to C plus L plus V. 1,000 is our feed and 35 is our vapor. Simplifying the equation will give us our first equation. For our water balance, the amount of water in the feed is 700 is equal to C times 7 times 18, the molecular weight of water, over 246.5, which is the molecular weight of our hydrate, plus L times 0.755 plus our vapor, which is 35. Simplifying the equation gives our second equation. Solving equations 1 and 2 will give us the values of our mother liquor, which is 704.28 kilograms, and the unknown in the problem, which is the value of the crystal, is 260.72 kilograms magnesium sulfate heptahydrate. Let us consider another type of problem. For our second problem, a solution containing 23% biomass of sodium phosphate is cooled from 313 to 298 Kelvin in a Swenson-Walker crystallizer to form crystals of sodium phosphate dodecahydrate. The solubility of sodium phosphate at 298 Kelvin is 15.5 kilograms per 100 kilogram water, and the required product rate of crystals is 0.063 kilograms per second. The mean heat capacity of the solution is 3.2 kilojoules per kilogram Kelvin, and the heat of crystallization is 146.5 kilojoules per kilogram. If cooling water enters and leaves at 288 and 293 Kelvin, respectively, and the overall coefficient of heat transfer is 140 watts per meter squared Kelvin, what length of crystallizer is required? Assume that for every 1 meter square area gives 1 meter length of the crystallizer. The following diagram illustrates the given problem, where F is the feed, L is the mother liquor, and C is for the crystals. Our required is the length of the crystallizer. Let us perform the overall material balance. Since we have no vapor, our material balance will be F is equal to C plus L. Simplifying the equation will be our equation 1. Getting the molecular weight for sodium phosphate is 164 and for its hydrate is 380. For the solute balance, the amount of solute in the feed is equal to the amount of solute in the crystals and in the liquor. Substituting the values, F times 0.23 is equal to 0.063 times 12 times 18, which is the molecular weight of the water, over 380, the molecular weight of the hydrate, plus L times the solubility, 15.5 over 115.5. Simplifying will give us our second equation. Solving equations 1 and 2 will give the value of our feed, which is 0.2854 kilograms per second, and our mother liquor, which is 0.2224 kilograms per second. To know the value of Q, or the heat, let us perform the heat balance, and it is indicated by the following equation. F times CPF times quantity TF minus TC plus CHC is equal to Q. Substituting the values, 0.2854 kilograms per second times 3.2 kilojoules per kilogram Kelvin times quantity 313 minus 298 Kelvin plus 0.063 kilograms per second times 146.5 kilojoules per kilogram is equal to Q. We will now have the value of our Q, which is 22.9287 kilojoules per seconds or kilowatt. From our previous learning, we know that Q is equal to UA times delta TLM. The formula for our log mean temperature difference is quantity TF minus T2 minus quantity TL minus T1 over Ln times quantity TF minus T2 over quantity TL minus T1. Substituting the values, we will have the value of our log mean temperature difference, which is 14.4270 Kelvin. Going back to our equation, Q is equal to UA delta TLM. Let us substitute the values. 22.9287 kilowatts our heat times 0.14 kilowatts per meter squared Kelvin, the coefficient, times the unknown area times delta TLM, which is 14.4270 Kelvin. We will arrive with the area 11.3420 meters squared. In the problem, we have the condition that for 1 meter length of the crystallizer corresponds to 1 meter square area. Therefore, the length is 11.3521 meters. To test if you fully understand crystallization, feel free to try this problem.
많이 사랑해 주시고요. 구호로, 특히 구호로 많이 사랑해 주세요. 감사합니다.